All right, kids, this is what we've been waiting for. Our very last Calc 2 lecture for the spring of 2020. 10.4, areas and arc lengths in polar coordinates. So what we have is we have some function defined in our polar coordinate system. We are now going to be having some area enclosed. Typically what we do is we imagine our ray going in the counterclockwise direction because that's how our angles increase. So we're going to span the area between two angles, but we're going to be stopped by our parametric curve. So this is the area that we're going to be looking for here. The area of a polar region is derived from the area of a sector of a circle. So I don't remember from your pre-calculus days that if we have a circle of radius r and we cut out an angle of theta, then the area is 1/2 r squared theta. So we're going to use that same template here where theta is going to be the distance between these two angles, and the radius is determined by the function, which varies as theta varies. So that being said, the area of this area right here is going to be, we're going to integrate, and what's changing is theta. So we're going to go, theta is going to change from A to B, and we're going to do 1/2, and instead of r squared, I guess we can call it r squared d theta. Right? It's also seen written like this, from A to B, 1/2. Well, r is defined by f of theta squared d theta. So this is the area of the circle, so don't confuse that for, so maybe I'll just do that. Right? This is our template for the area inside a region between angles defined by r equals f of theta. Okay, so let's look at an example. These get a little bit tricky. Let's suppose we wanted to determine the area of the inner loop of the Lamicon, r equals 2 plus 4 cosine theta. So it's understood we're looking for this area right here. So I'm giving you the equation for this, but the problem is we aren't given the bounds. Sometimes you're given the bounds, other times you have to figure it out. So this is one of these examples where we want to know what values of theta, what are we going to do? So my area is we're going to integrate 1/2 this guy squared. But the problem is we don't know our limits of integration. Well, we can just imagine how when this guy goes around, anytime we go through the origin, r is 0. So this goes through the origin. It goes through the pole. I'm going to call it when r equals 0. So what we're going to do is set this equal to 0, and we'll see what's going to happen. 4 cosine, I'm going to find our bounds for theta. When does 2 plus 4 cosine theta equal 0? We're going to subtract 2 and divide by 4, and that's equivalent to solving the cosine of theta equals -1/2. Right? So if we imagine swinging this guy around and we do this, how long is it going to take before, we get to there? So it's going to be answered here. So theta is equal to, well, what angles from, we start at 0 and we scan around, have cosine equal to -1/2? Well, 120 degrees and 240 degrees should do the trick here. Now, one thing you can do is you can graph this. Let's pull this up and graph this guy and see what we have here. And this isn't a bad idea. This is 2 plus. It's always a good idea to take a look at what we're doing. So if we just graph this guy, I'm going to go to my window. I'm going to go from like -2 pi. Nope, don't do that one. 2 pi to 2 pi. I'm going to see what this guy looks like. Whoops. Oh, we don't want to do that. Y equals, let's go to my window. I'm going to do zoom. Let's do zoom 6 and see what happens. There we go. All right, there it is. So there's my guy. All right, so now I'm seeing, my guess is that this is going to just create that inner loop from 120 to 240 degrees because that's what solved that equation, and that's where it's going to go through the origin a couple times. So I'm going to go back into my window and I'm going to see what happens. All right, let's see. I am in radian mode, so I have to put these in radians, or I can just simply go into degree mode. Typically when we're evaluating these, we should be in radians, but for the simplicity of it, I'm going to go from 120 degrees to 240 for now. And if you notice, that gives me nothing. Nope, let's go back to mode. I'm going to go back into radian mode, and I'm going to go window. My minimum, I'm going to do, well, let's try 2 pi divided by 3. And we're going to go to 4 pi divided by 3 because that's what those two angles are. All right, and let's see how this goes. All right, we're still not getting in there. Let's see, zoom. 6, I just had it a minute ago. Right, there's my whole guy right there. My window. Oh, now it is. I have from 0 to 2 pi. So that's 0 to 2 pi. I'm not quite sure why it's not pulling that up for me. I know that it's right. 2 pi divided by 3. Divided by 3. All right. Oh, you might just have to trust me on this one because I'm not sure what I'm doing wrong. 4 pi divided by 3. Let's graph it again. Oh, there we go. I don't know why it didn't come up that time. So there we have our little inner loop right there. So let's just zoom in and see that guy. There we go. So there's just our inner loop right there. And that's what we want to know the area of. So we really should work in radians. So let's call this 2 pi over 3 and 4 pi over 3. There we go. Works much better. So these points define where the inner loop starts and ends. So it is our integration limits. So if we go to our template, that shaded area is going to be from 2 pi over 3. And then we span all the way to 4 pi over 3. It's going to be 1/2, and then it's going to be the equation. It's just the equation itself, squared d theta. All right, let's see if I can do this without making an algebra mistake. All right, so I'm going to actually square this out. I'm going to pull, I'm not writing the limits of integration now just to not create a big mess here. So this is going to be 1/2. I square this. Don't forget to FOIL. 4 plus we get 16 cosines. All right, plus we're going to have 16 cosine squareds, d theta. So we don't, it's all positive, so that's pretty nice. I'm going to distribute this 1/2 through because everything is even, so that works out very nicely. So 2 plus 8 cosine thetas, both of those are really super easy to integrate. 8 cosine squared, if we remember back to our trig integration, this shouldn't be a big deal, okay? So we're going to replace cosine squared with 1/2 1 plus cosine of 2 theta to integrate that easier. So I'm going to continue this on the next page. Let's see if I can put that up here and still see it. Nope, you can't. So let me try to pull it down a little bit. That is where we are. All right, so we are at, and I'm leaving out my limits of integration. I know it's improper, but it's just saving a lot of writing in a big mess. Cosine theta, and I'm going to distribute the 8 through, which actually is 8 times 1/2, which is 4. So it's going to be plus 4 cosine of 2 theta. And I'm just going to combine those constants just to leave one less term. We have a lot of stuff to stick in, so we're really actually integrating from 2 pi over 3 to 4 pi over 3. And we are integrating 6 plus 8 cosine of theta plus 4 cosine of 2 theta d theta. All right, now we can actually integrate. All right, the antiderivative of 6 is 6 theta. 8 cosine theta would be just 8 sine theta. Be careful with your signs. The derivative of the sine is positive cosine. And then 4 cosine 2 theta is going to be, well, this would be 1/2 sine 2 theta, but the 1/2 and the 4 make 2 sine 2 theta. And we evaluate that from 2 pi over 3 to 4 pi over 3. All right? So make sure you take the derivative of 6 theta theta. 8 sine theta is 8 cosine theta. 2 sine theta. 2 sine 2 theta is 2 cosine 2 theta times 2, right? So now I'm going to let you plug in the details for practice. And I got 4 pi minus 6 square root of 3. So fingers crossed that that is our area. So that should be this area right here. All right. All right, let's try one of a little bit different of a caliber. Let's suppose you are asked to define the area that lies inside this guy. another Lamicon, and outside r equals 2. Remember, r equals 2 is just a circle, so that's the green circle, r equals 2. This is 3 plus 2 sine theta. Feel free to graph these guys. Let's see if I can do this. I'm going to try one more time, and if I fail the first time, then I'm just going to put the calculator away for this semester. Let's see, sine theta. All right, and then we're going to do 2, r equals 2. I'm going to do, let's just graph and see what comes up. Nope, graph. All right, all right, so it doesn't look what I want it to look like. So first I'm going to do zoom standard. So I'm going to go back to my standard rectangle. There we go. And there's my other one. So there we go. It looks pretty good. We can't see quite the details down there. If you want to zoom in at the origin, we can do that and kind of maybe we can get a little better of idea. So we can kind of see the little bump. I just exaggerated it. Right, and then the circle. So we want to find the area that lies inside the purple shape but outside the circle. So in other words, we need to find this. So you're welcome to be creative, maybe using the intersect button on your calculator. We have to find these 2 points right here. We want to know where do those curves intersect. So what we do is we just simply set them equal. Points of intersection, just like we did in Calc 1 in 6.1. So we do 3 plus 2 sine theta equals 2. So 2 sine theta equals -1 sine theta equals -1/2, right? So what angles give me sine -1/2? Well, theta is going to equal, theta is going to be sine is -1/2, so it's got to have a reference angle of 30 degrees. So this, if it's a reference angle, I know I'm a little bit off, but a reference angle of 30 degrees would be 210 degrees. And then a reference angle of 30 degrees over here would be 330 degrees. Right, so let's convert these. I'm going to do 7 pi over 6, and we'll call this guy 11 pi over 6. All right, now I'm going to draw these in because these actually aren't both the angles that we're going to use. So this angle right here, this is when theta equals 7 pi over 6. And this angle is when theta equals 11 pi over 6. Now the problem is if we use these 2 angles, we're going to be swiping between 7 pi over 6 and 11 pi over 6. So if we swipe between 7 pi over 6 and 11 pi over 6, notice that's going to be from here to here, and it would give me this region in here, which is not what we want. So what we actually need to do is we want to swipe from here all the way over to here, but we want this angle that we start with to be bigger than the angle that we end with. So if we go from 7 pi over 6 to 11 pi over 6, it's going to give us the wrong region. So this angle can also be represented by -pi over 6. So it definitely comes with a few extra tricks here. So just be really careful and feel free to zoom in if you want to talk about it. All right, so let's go. We're going to use -30 degrees or -pi over 6 as our integration limits. So the area is going to be found by integrating -pi over 6 to 7 pi over 6, and it is 1/2, and we're just going to integrate. We're going to find the area inside the whole shape and then subtract the white area. So we'll do 3 plus 2 sine theta, and then we're going to subtract this area, which would be the area from -pi over 6 to 7 pi over 6, of just, squared. And then we would be doing that area squared. So it's the outer area minus the inner area, and then we're going to integrate with respect to theta. So outer minus inner. Is that how you spell outer? You know what? It doesn't matter. You know what I mean? Okay. All right, so let's do this. This is going to be, again, I'm going to leave off my integration limits just because it gets messy very quickly. So this is going to be 1/2. And I'm going to do, this is going to be 9 plus 12 sine thetas plus 4 sine squared theta minus 5 d theta. All right, let's see, do we want to, I'm going to pull that 1/2 out because we have some odd numbers in here, do we? Yep, nope, sorry, that's 4. Don't do that. So then we're going to have 1/2. We're going to just be integrating 5 plus 12 sine theta plus 4 sine squared theta d theta. We can do this straightforward, this straightforward. This is going to give us a little bit of a problem. So let's replace sine squared theta with 1/2, 1 minus the cosine of 2 theta. All right, and rewrite this 1/2. We'll integrate 5 plus 12 sine theta. Bring the 4 through and distribute. So 4 times 1/2 becomes 2. So that is going to be 2 plus 2 minus 2 cosine 2 theta. So one more simplification. Combine that 5 and that 2. We get 7 plus 12 sine theta minus 2 cosine 2 theta d theta. Oops, I should be consistent, right? So now let's integrate. We'll have 1/2 7 theta plus, nope, it'll be minus 12 cosine theta. And this will be minus cosine, how about the sine of 2 theta? All right, so 7 theta, that would be that, that's going to be that, and we're going to evaluate that from negative pi over 6 to 7 pi over 6. And again, to save time, I'm going to let you work out the details. And I got, and hopefully you too, 11 square roots of 3 over 2 plus 14 pi over 3. I know, lots of work, lots of things to remember. All right, one more topic. Arc length. The length of a curve with given polar equation. So the length of a curve, within this, the derivation of this is quite lengthy. Feel free, you can turn to page 672 in your book and see the derivation of this. The length is given by, if you notice, this will be similar to the length, arc length that we did when we were looking at explicit functions. So it's going to be the square root of r squared plus the derivative of r with respect to theta squared d theta. Right. So I'm going to leave it at that. You are welcome to read about it and ask questions if you want to talk more about the derivation. Right. So this one's so cool. It looks so simple. It is so simple, but it's just beautiful. Let's look at the curve r equals theta. I'm going to just go from theta equals 0 to 1 for simplicity. R equals theta is just this spiral. It's so super cool because if you think about it, if you go for every measure of the angle that you go out, r increases by that. So if r is 0, we're right here at 0. If r and theta are both 0. If theta is 90 degrees or pi over 2, we're going to be right here. Pi over 2 is about 1.7. If theta is pi, we're going to be right here, a little past 3. R will be a little past 3, and then we can continue around. And it's just going to keep expanding. Now, in the sense of the area or the length that we're looking for, not all that interesting. I'm only looking for a little piece right here. I mean, we can go from, this would be pi, this would be 2 pi, this length would be 3 pi, so forth and so on. But for simplicity and plugging in at the end, I decided to just stick with 0 to 1. Okay, so the length of this curve, just between 0 and 1, we're going to integrate from 0 to 1, and it's going to be, well, r is theta, r is equal to theta, and dr is just equal to, dr d theta is just equal to 1. So we really just have theta squared plus dr d theta squared, which is 1 squared, which is 1 d theta. So look at that super cool little integral that we get to do. Does this look familiar? Trig sub. We let theta equal tangent, then d theta equals secant squared dx, right? And then the square root of theta squared plus 1 is going to be the square root of tangent squared plus 1, which is the square root of the secant squared of theta, which is just going to be the secant of theta. So integrating the square root of theta squared plus 1 d theta is equivalent to integrating. Oh gosh, I know. Theta, this is going to be the x. Don't do this because we're going to be doing this, right? There we go. Tired. I'm almost done though. So close, right? So we're really going to be integrating. Integrating theta squared plus 1 is equivalent to integrating secant squared of x. And then d theta is, or secant of x, secant, there's my secant squared of x dx. So really just integrating secant cubed of x dx. That's it. All right, so at this point, I was like, we could do this using all our trig identities. I took the shortcut. I used the tables, so go into your tables, and you'll see that this just equals 1/2 the secant of x tangent of x plus the natural log of the absolute value of the secant of x plus the tangent of x. All right, now here's where it gets tricky. What are our integration limits? I started with the integration limits. Note, we started with 0 to 1, but that was d theta. So theta goes from 0 to 1. So there's a couple things we can do here. We can use the fact that theta equals the tangent of x, and we can put theta here and here, and then we can find the secant using our triangles. Yeah, let's do that. The tangent of, so inverse tangent, yeah, we're going to do that. Inverse tangent of theta equals x. So I'm probably going to kick myself for doing this because I did it the other way in my notes, but let's go. Here's theta, right? So it's going to be x over 1, and then this is going to be the square root of x squared plus 1, right? So then the secant's going to be, all right, so let me just make sure I did that right. R squared. Okay, so the secant's going to be, the secant's 1 over the cosine, so it's going to be the square root of x squared plus 1. All right, so let's put that, the secant of theta is that, oh my gosh, why am I doing this backwards? Inverse tangent of theta, so the secant of theta, nah, I'm going to do it the other way because it was a lot easier. So, all right, sorry, you guys can do that if you want, but I'm literally just so burned out. All right, so theta goes from 0 to 1, keeping in mind that we let theta equal the tangent of x, right? So if theta equals 0, that tells me 0 equals the tangent of x. And what does x equal? Well, x is equal to 0 because the tangent of 0 is 0. And if theta equals 1, then 1 equals the tangent of x, and x is equal to the angle pi over 4. So I'm going to use that because that's a lot easier to stick in here, and I'm going to do that, so I apologize. I should have just done what I did originally. So we're actually going to stick in secant of x, tangent of x, plus the natural log of the secant of x plus the tangent of x. Right? And then we're going to go from 0 to pi over 4. So I'm going with that trick that I typically don't do, and that is change the integration limits because it seemed easier at the time, and clearly it was because I messed up when I did the triangle. But I challenge you to do it with the triangles and see if you get the same answer. So we're going to put in our pi over 4, right? So we're going to have 1/2 the secant of pi over 4, tangent of pi over 4, plus the natural log of the secant of the pi over 4 times the tangent, or plus the tangent of pi over 4, right, minus 1/2, and we're going to get minus 1/2, and I have the secant. I should have just let you guys do this. I'm going to let you finish it up. Tangent of 0 plus the natural log of the absolute value of the secant of 0 plus the tangent of 0. Right, and I got, working out the details when I did it here, I got the square root of 2 over 2 plus the natural log of 1 plus the square root of 2 over 2. All right, see if you can get this. I'll redo it again afterwards. I'm hoping that's right. All right, kids, that's it. Congratulations. You survived my online videos. You deserve a high five and a big reward for that. Read 10.4 exercises. I don't know. I haven't gone through too many of these. 1 to 41. Every other odd. I mean, pick at them. Do a few. Make sure you know you're doing the ones in XYZ, 45 and 47, and 7.4 XYZ. That's it. Woo-hoo. Happy summer, kids. Talk to you soon.